Now, in this particular video lecture, I would like to make an attempt. I will like to make an attempt that what are the techniques or how we can actually plot or draw the space distribution of armature MMF and space distribution of field MMF for a DC machine. That means we want to know the space variation or the space distribution of armature MMF and space distribution of field MMF. This is we want to know. Now, before we embark upon the process, let me tell me few things which are related with this diagram. Then I will move over to the develop view. Actually, whenever we are asked to plot this space distribution of MMF of a winding, we should take develop view. What is the meaning of develop view? Develop view means nothing. We are imagining that this part will be cut and it will be straightened. That means you are going to imagine that the portion of the DC machine is being cut from a place, and then we are making it straighten or flatten. That is the develop view. Or you can say DC machine being cut and laid flat. That is, let's say if you have a, what should I say, circle. So what is the develop view? You cut the circle at one point and straight it, so it will become a line. If you have a some sort of structure which is a cylinder, so what is the develop view? You cut the cylinder at one point and then you make it flat or straight. But before we take the develop view, let me tell you one or 2 points. What are those things? First is that we should make ourselves very much clear that what is the nature of field winding. We should also make clear what is the nature of armature winding. The field winding is actually concentrated winding. Field winding is concentrated winding, whereas armature winding is distributed winding. So what is the difference, or rather what is the meaning of concentrated winding and distributed winding? See, in order to figure out that, let us first think of a coil. Let's say this is the shape of a particular coil. This is more popularly known as diamond shaped coil. You can see the shape. So this kind of coil is known as diamond shaped coil. So in this coil, this part is known as active length. This part is also known as active length, and this part is known as overhang or end connection. Okay, this part is your overhang and this is your end connection. So this portion of the coil is known as active length. This portion, if you allow me, I will write the name so that it's easier for us to communicate. Let's say if this is A, B, C, D. Let's say this point is E, and we just say F and G. F, G. So what are F and G? F are G. F and G are the two ends or the two terminals of this coil. AB is the active length, this part. AB is the active length of the coil. Likewise, CB is also the active length of the coil, whereas AE and EC is known as overhang, and F and G is the two ends or the two terminals. F and G are the two terminals of the armature coil. These terminals of the coil, armature coil, will be connected to commutator segments. In case of DC machine, these two ends of the coil, F and G, will be connected to two commutator segments. If it is lap winding, in that case, F and G will be connected to two consecutive commutator segments. Now, why AB and CD are known as active length? Because this part of the conductor is going to link the magnetic lines of flux. AB and CD, this part of the conductor is going to link the magnetic flux. That's why they are known as active length. AE and EC will also link magnetic flux, but that is mainly leakage flux or overhang flux. They are not going to link the main flux. AE and EC part of the coil will also link magnetic flux, but that is leakage flux or overhang flux. That is not the main field flux. Main field flux of the DC machine will be linked by this portion AB and CD, because this is a cross-sectional view. So you can imagine that conductor AB, let's replace this coil by this one. It's easy for us. let's say this portion is your AB and this portion is your CD. So this is your CD, this is your AB. So the coil is like this. So this portion is AB, this portion is CD. So what is the magnetic axis for this coil? See here, let's say this coil is coil 1 dash. I guess you are able to see coil 1 dash. So this is 1 dash, this is 1 dash, and this is 1. So this is coil side 1, this is coil side 1 dash. So cross means what? Current is entering into the board, and from back of the board it is coming out. Dot means what? Dot means it is leaving the board. You just focus here. 1 is cross and 1 dash is dot. Cross means current is entering into the board. 1 dash means current is leaving the board. So this is my coil. This is coil side 1. This is coil side 1 dash. So you apply right hand rule. This right hand 4 fingers will be directed along the direction of current. So you see where is my thumb pointing? My thumb is pointing in this direction. So the magnetic axis for this coil 1 dash is in this direction. Okay? Let me draw it separately. So let us try to find out. So this is coil side 1. So coil side 1. This is coil side 1 dash. So coil side 1 dash. This coil side 1 is carrying cross current. So here cross. Coil side 1 dash is carrying dot current. So here dot. So what I was saying, so let's say this is coil side 1 and this is coil side 1 dash. So this is the plane of the coil. This is the plane of the coil. Cross means what? Current is entering into the board. Dot means leaving. So where is my thumb pointing? In this direction. So the magnetic axis for this coil will be in this direction. I guess you have understood. It's very easy. You apply that right hand rule. Cross means entering into the board. Dot means leaving. So where is the thumb pointing? In this direction. Right? Thumb is pointing in this direction. So this is the magnetic axis for coil 1 dash. In the same way, you have to find the magnetic axis of coil 2 dash, 3 dash, 4 dash, 5 dash, like that. So you will find that the magnetic axis for coil 1 dash and for 2 dash, they are not aligned. They are separated in space or distributed in space. That's why we call that the armature winding of a DC machine is distributed winding. Why we call distributed winding? Because if you find the magnetic axis for each of the armature coils, you will find that the magnetic axis for each of the armature coils are not aligned in space. Rather, there is a shift, there is a angular shift between the magnetic axis of different coils. Let me draw once more so it will be clear to you. Let us take coil say 3 dash. So what is the orientation of coil 3 dash? Coil 3 dash is like this. This is 3. Okay, let me better you take another coil. Let's say coil 5 dash. I am taking 5 dash. So this is my coil 5 and this is your 5 dash. So what is the current carried by coil side 5? Coil side 5 is carrying cross current and coil side 5 dash is carrying dot current. So what is the magnetic axis for this coil? Dot means leaving the board, cross means entering. So you see the magnetic axis for this coil side 5 dash is directed in this direction. Cross dot, or you can say dot cross. So you see the magnetic axis of these two coils, namely 1 dash and 5 dash. You can correlate. 1 dash means this coil 1 dash and coil 5 dash means this one 5 dash. They are not aligned in space. There is a angular distance between the magnetic axis of these two coils. The same thing can be easily observed for remaining 4 coils. I have done it for 2 coils, 1 dash and 5 dash. You can take the same approach and find the magnetic axis for coil side 2 dash, 3 dash and 4 dash. You will find that and also for 6 dash. You will find that the magnetic axis of the coils are not aligned in space. That's why we say the armature winding of a DC machine is distributed in space. Distributed winding means the magnetic axis of the different coils are not going to be aligned in space. Rather, the magnetic axis of different coils will be separated in space. There will be some angular distance between the magnetic axis of the corresponding coils. Over here 1 dash 2 dash is like that. But what about the meaning of concentrated winding? In case of concentrated winding, you will find that magnetic axis of all the coils will be aligned in space. Let's take the field winding. Field winding of a DC machine. Field winding of a DC machine is an example. Field winding of a DC machine is an example of concentrated winding or concentric winding. You see here, if you take these 4 coils cross and these 4 coils dot, the magnetic axis is coming in this direction. Now you take this layer. Let me name it so that it's easier for us to communicate. Let me name it. Let's say this is layer number 1, layer number 2, layer number 3. So this is 1 means this will be 1 dash, 2 dash, 3 dash. So you take the first layer of field winding. First layer is which one? 1 dash. First layer is 1 dash. What is the magnetic axis? In this direction. You take the second layer. Second layer is which one? 2 dash. What is the magnetic axis? In the same direction as that of the previous. That is 1 dash. Again you take the third layer. 3 dash. What is the direction of the magnetic axis? In the same direction as that of the previous two. That is 1 dash and 2 dash. You see here, the magnetic axis for all the coils are aligned in space. That is, they are in the same line, same direction. So that's why field winding is concentrated winding or concentric winding, whereas armature winding is distributed winding. So this was about the nature of the field winding and armature winding in a DC machine, but we are interested in finding the space distribution of field winding and armature winding. So for that, what we have to do, we have to take the develop view. So in develop view, what has to be done? We have to imagine that we are cutting the machine at some point. So let us start with first armature winding. We want to find the space distribution of armature winding, MMF, armature winding MMF. What is the meaning of space distribution? Space distribution means nothing. You go on measuring the strength of the armature MMF at say this point, at 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 this point. Likewise, you are going on measuring the strength of the armature MMF along the air gap periphery, along this air gap periphery. So you are measuring armature MMF strength over here, over here, over here, over here, over here. Likewise, you are going on measuring. So what we have to do is that we can measure this angular distance along the air gap periphery in terms of some angle theta. What is this theta? Actually, it's a mechanism by which we can pinpoint or determine a particular point in the air gap. What you have to do, you have to just select a reference axis. Let's say this is our reference axis. This axis which is passing through the polar axis, this is our reference axis. So if this line which is passing along the polar axis, if this is our reference axis, so value of theta will be 0 here. So here at this point, what is the value of theta? Theta is 0. So over here, what is the value of theta? Over here, theta is 90 degree. Okay? Let me write it over here. Theta is 90 degree. Isn't it? So what we are doing? We have defined a reference axis. Okay? Nothing else. Very simple. We have only defined a reference axis. Let's say this is our reference axis. The line, imaginary line passing through the polar axis or the direct axis, this we are taking as our reference axis. So along this line theta will be 0. So over here theta is 90 degree. Over here theta is how much? Obviously it is 180 degree. Over here theta is how much? Obviously theta is 270 degree. Over here again it is 0 or 360. So you see, by just defining a reference line, we are able to locate any point along the air gap periphery by just the value of angle theta. Say if you want to locate or if you want to identify this point, let's say this point, we want to identify this point. So how to identify this point? this will be theta equals to say 30 degree. Okay, this will be equal to say theta equals to 30 degree because it is at an angular distance of 30 degree from the reference axis. Likewise, this may be theta equal to 60, this is 90. Okay, so this is a very convenient way of pinpointing or determining the different points along the air gap periphery. We define a reference axis. With respect to reference axis, we are measuring or we are trying to measure the angular distance of the different points. So what is our aim? Our aim is to determine the variation of the armature MMF along the air gap periphery, or you can say space angle theta. This theta can be termed as space angle because it is helping you to locate or pinpoint a point along this space. Here by the word space we mean the air gap between the stator and rotor, or between the field pole and the armature core. There is a air gap between field pole and armature core. That point or that portion is, we are using the word space. We are referring the word space for that. So in order to find the armature MMF variation, we need to take the developed view. But for taking the developed view, we have to imagine that we are cutting the armature core at some point. So where we will be cutting? We will cut the armature core, listen it carefully, we will cut the armature core at that point where no magnetic lines of flux are leaving or entering the armature core. Please look here, what you see, that between slot number 3 and 4, no lines of flux is either entering or leaving. Likewise, please look here, between slot number 3 dash and 4 dash, no lines of flux is either leaving or entering. So we will imagine that the armature is being cut along this portion. If you want, or if you are interested in finding the MMF distribution of armature winding along the air gap periphery, you have to take the developed view. For taking the developed view, you have to cut the armature core. So we will cut the armature core at this point between 3 and 4. Why between 3 and 4? Because no lines of flux is entering between 3 and 4. You can argue that we can also take the developed view by cutting it along between 3 dash and 4 dash. That can be also done. I am cutting it over between 3 and 4 dash. So what is, imagine that armature core is being cut between 3 and 4 dash, and I am holding this part, this top portion with my left hand and this bottom portion with my right hand, and I am making it straight. So slot number 3 will come here, then 2, 1, 6 dash, 5 dash, 4 dash, that way. Okay. Now, how to take the developed view for finding the field MMF distribution? For finding the field MMF distribution, again we have to take the developed view. So for doing that, what has to be done? We need to see, that along which portion the field flux is neither leaving or entering the armature core. So at which point the field flux, please look here, look at the diagram, at which point the field lines of flux at which point is neither entering or leaving the armature core, that is along the interpolar axis. So if you are interested in finding the field MMF distribution or the space distribution of field MMF in DC machine, then you have to take the developed view along this interpolar axis, because along interpolar axis the field flux is almost zero. So we will cut at this point and then we will stretch it and make it flat. So you imagine that this portion being cut here and then you are stretching it and making it flat. Let's say you are holding this with your left hand and this portion with your right hand, and then you are making it straight. So what will happen? Pole tip Y will be coming here, pole tip Y dash will come here, then pole tip X dash, and then pole tip X, like that. Okay, so let me draw it, but you need to remember what I have said. For armature MMF variation, you have to take the developed view of armature, you have to cut the armature core, at that point where no lines of flux is entering or leaving the armature core. Now, which lines of flux I am talking about? It has to be made very clear. Armature lines of flux or armature flux. This magnetic flux is not due to field current. Please remember, this magnetic flux is not due to field current. This magnetic flux is due to armature current only. So we have plotted the magnetic lines of flux corresponding to armature current, and we have seen that armature flux is neither entering or leaving this part between slot number 3 and 4. Between slot number 3 and 4, armature flux is neither leaving or entering. So we are taking the developed view by cutting the armature core at this point between 3 and 4, and then we will make it straight and straighten it. Okay, so let me draw it. I will be drawing it. Then again